Okay.
Okay, so thank you for coming. My pleasure to introduce first of all, we have 3 international speakers in the next 3 weeks. So I don't know what's happening in Perth. Well, I know Oakley's happening in Perth, and that's why Kathy's here. But I'm not quite sure why we're getting so many people coming to Perth suddenly. But it's my pleasure to welcome Sudeshna, who will be talking about evolution and charts.
Okay. Right. So just a little bit. So first, I sort of just realized that I have like 40 minutes. I'll try and keep myself within that. Okay. Yeah, if I spill in a bit, just stay with me. Okay.
If you talk too long, Thomas will get you wrong.
Okay. I'll live with that.
No one can tell the difference.
Oh. Right. Well, okay. Yeah. So anyway, so I thought I should flash a little, 4 boxes to show my institute. This is IISER, and there are 5 of them, like north, south, east, west, center, and ours is in the north. So we are up there, cooler climate, closer to the hills. It's a good place to visit. Yeah. So do come by. Okay, and here's my website in the unlikely event you want to know a bit more about me. Very unlikely, but in case you want to do it. Okay, so what I thought I'd do is try and share some results with you. These are all very recent, as you can see, just this year. So fresh off the mill in some ways. And I will only sort of, run by stuff of the first paper. And the second one, maybe a little elevator pitch of 2 minutes to tell you how it ties up with the other one. Okay, so mostly on the first one. And Manish used to be my student actually, and now he's a postdoc with Martin. And Anil is sort of mentored by me, is now a postdoc in Carnegie Mellon, or will be, if his visa goes through. Yeah, okay. So first a disclaimer, and that is I really am not an expert in ML. And certainly not in reservoir computing. I just took a fancy to it like a couple of years ago. So I'm really kind of getting interested in it. So by no stretch of the imagination, I'm an expert. I thought I'd share this set of results because I think there may be more people in the audience where it might resonate with. And so I suppose I've chosen the topic more because of the expertise of the audience rather than my own expertise. Okay, we'll see how it goes. So I'll be a bit outside my comfort zone, but let's see. Okay, so the first thing is the simple stuff, but let me just put it out there. So artificial neural networks are universal function approximators. This is the good news. Okay, this is the stuff which we put out there to get the money, to get our students to work on stuff. And it is true. There's nothing untrue about the statement. And it can be used, of course, for lots of tasks like forecasting, which we in dynamical systems know and like. Okay? But though it is, of course, a very powerful tool, we all know it, and it's like in everywhere from popular press to academia, it actually might in practice need an impracticably large number of neurons to do the task, to the accuracy which you can think of as a reasonable one. Okay, and that is not the only thing. One of the serious drawbacks which I always felt, which sort of for me personally, it was a deterrent to even trying or getting interested in the stuff. And the thing was that a lot of machine learning algorithms, it does not have a priori estimate of how big the network should be in order to be effective. It doesn't have a priori idea of many things, but this is one of the big things which you don't have. So if you have a big machine, you throw 100 at them. If even bigger machine, you throw 1,000 at them. It's a bit of word of mouth. It's, somebody's a water cooler gossip, which tells you how much is good enough. Okay, and so mostly it's case by case. And if you had to do it systematically, it also doesn't make sense because it's like a very large hyperparameter space. Okay, so in principle, it can only be very sparsely explored. Okay, so this is what is at the back of our minds when we started this. So one of the things would be, it would be nice if we could sort of gauge how big is big enough in some general fashion Or how can we even arrive at something that's big enough? That is not too big, that is. I mean, if you throw everything at it, it'll work, but how big does it really need to be? So that's one of the applied sort of questions. But, you know, from people who are not so applied like me, one of the things which is of interest is that, maybe there's some underlying concept into building these small effective networks. So what is that? And if you can get some, like an adaptive principle to grow the network, starting with a few seed nodes, say like 2 nodes, and see how much it grows up to do the task. If it was like 1,000, then you've really gained nothing. But suppose 5 nodes do it, then it's a lot of fun. So this is what I would try and get across. And so it would allow this sort of synthesis or like a designed small network with, of course, the computational capacity of what you would typically use, which is a large amount. Okay, and the other angle of it, which is not the applied angle, but more trying to understand the box angle. So ML is this box, but suppose you wanted to somehow think of it as giving some function. What would be the structure of your box? So if you grow it, these boxes are small then, and so you could probably get some idea of, is there a special type of box that it evolves to, which is different from a random sampling of these boxes. So this is one of the questions which we will try and figure out. And so in some sense, what we have called it is a performance dependent network evolution, and in a minute I'll explain the algorithm to you. And this part is using reservoir computing, partly because it's so neat. It just it's very easy to think of it in terms of dynamics. But Anil in the US has also done it for feed-forward neural networks. It's a little harder there because that's more like a function. This is more like a dynamical system. So I thought I'll only run with this for this talk. Okay, so the bottom line up front, at this point, if some people want to leave, it's perfectly okay. The rest of it is going to give meat to these statements. Okay, so what we found was, this is just like literally the advertisement for the rest of the talk. So what we found was that these evolved networks outperformed, like without doubt, a random network, and bigger was not better. In fact, these evolved networks were really very small. In some of the tasks, it was as small as 5, 10, 20, really small. Okay? And they gave as good a result as 100 or 1,000 sized networks. And so this was the first good news. And the other part is more observational. You look into it and see, like, is there anything that pops out, that looks different from this evolved network as opposed to like a random network. And one of them was sparsity, and the other one was a scaling law in the node density space. I will show you a picture where it literally visually the scaling law comes out. And so if you think of the space of this node density space as a 2D thing, the scaling law essentially constrains it to a 1D curve. So you see how special these things are in this space. Okay, and the last thing is a kind of asymmetry in the input and information readout node distribution. None of these were things we put in by hand. All of these were things which came out of the algorithm. Okay, these two parts. The first one, of course, was why we continued with it. Okay, so reservoir computing. One quick slide to have everyone, experts all here, but maybe some people are not that much into it. I wasn't a year ago. So here it is. You can always think of it as this fat blob in the middle is your reservoir, okay? And it needs 3 things. You have to give it some input, the reservoir does the heavy lifting of computing, and it spits out an output. So there has to be an output layer, there has to be an input layer. The world gives you one, output layer is the world takes that one, and the stuff in the middle is what is kind of like a recurrent neural network, okay? And this is the broad sense in which you can visualize it. And if I had to write it in one summary equation, it would be the one in blue. Okay, so the dynamic input signal is some U is fed into the reservoir, and there is a simple readout mechanism which is trained in order to obtain the mapping. So think of it this way: where is your training done? Only in the readout. This is one of the reasons why dynamical systems people like it, and of course engineers don't like it that much, because you really don't train the reservoir. The reservoir is what it is. You train the last output layer. Okay, so these are, I have sort of spelled out all the symbols out here, and essentially this is, oops, I don't know how to, oh, does this work? Maybe not. Okay, I shall wave my hands around. So essentially you will have this kind of output weight matrix, which you're going to minimize the difference between the reservoir output and the actual output, the ground truth. Okay. So if I look at it one more time, a key feature of this is that only the readout, as I said, is trained. Okay. The reservoir network stays fixed. Okay, this is one of the things. Is there, you mean a pointer? Oh, okay, thank you.
Proper teacher is going to point to this.
Okay, after saying yeah, there is something red out there. Okay, right, thanks. So here is, so this is one of the key features of the reservoir computing thing, which is why actually it's so tempting to use it like a test bed or a, a kind of place to do fun things with. Okay. Because you can literally sort of separate out your computing machine part and the stuff which the humans do with it. Okay. And another picture which Manish had made for me, so I should, okay, clearly I'm not good at this either. Here, okay, right, it's the one on top. So here is this. So this was the R, which I had put in the equation before. These are the W's, the in, the out, and you might give it some dynamic input and expect a certain output, and of course the response has to adjust itself in order to nail it. Okay, so what are we proposing? So we are saying, okay, let's sort of, the key idea is to get some evolutionary growth of the network. And how would you, growth of course means adding stuff, right? Because you have to make it bigger and bigger. And in that sense, it has to have a part, a module, which adds nodes, okay? But if it added nodes just like, I keep slapping in more and more and more nodes, then I might as well have begun with 100 and, gone on with it. So you want to do a little more than that. So you want to add a node to the existing network only as long as the overall information processing capacity is improved. So you're not going to get another node in unless it's working for you or doing something for you. Okay, so no freeloaders in your reservoir. Okay, and the second part, we went with this adding part and we thought we would get good results. We got okay results, but not like spectacular results. What then happened was we thought, okay, maybe in the network we also need to fire and give pink slips to the obsolete or the useless nodes. Okay, so think of it this way: when I add a node, stuff gets rearranged, and actually some nodes value decreases, so it goes obsolete or useless, and so you might want to remove it. So we not only add, we also have a removal mechanism so that we can prune it at every micro step, saying that okay, if you're not adding to the value, you are out. Okay, it's sort of like the management, I suppose, a business model of the of your reservoir. Okay, and this node deletion actually we found was a crucial part, because I know we had not thought of it also, and so we need both these things, the addition and the deletion. Okay, so how does this look? Let me draw it in 3 figures. So addition module. So these are two modules which are kind of, you can put it in the flow chart. So one is you add in some node, you evaluate the performance. If it is not doing better, you don't take it. If it's even doing equal, you don't take it. It has to do better. Okay. So you have this kind of, say for instance, maybe mean square error or normalized mean square error, something which gives you an evaluation, and after that, if it doesn't pass the test, you don't accept it in your club. The deletion is after you have grown the thing a little bit, you go back and take a sort of stock and a little evaluation test again. Okay? Nobody is safe again. So you randomly pick up nodes and you delete it and you see if you do better or worse. So if you do even equal amounts, it means you were not necessary because you didn't, improve things. So it gets chucked out. And so these two modules, the addition and the deletion, kind of orchestrate overall network evolution. You retain only those that improve and eliminate those that don't assist, and in the process you grow, but you don't grow unless you deliver. Okay, so this is like one line summary, one long line summary of what I said. In a nutshell, modules A and D will orchestrate the growth of the network, and it hopefully does it in a way that it improves the information processing capability and works to retain only the nodes which assist, okay, and eliminate those that don't. Okay. It's a flow chart of the algorithm. All of this is on GitHub, as it must be, of course, nowadays. And Manish also curates a good many of little additions and, more efficient versions of the same. And so essentially, whatever I've said, I've written it down as an algorithm. And at the end, we always started with 2 nodes. And 2 nodes didn't cut it for any task. So 2 nodes was just not big enough. The minimum one was about 5, but we always start with 2 and we start growing it. And say for a certain task up to a certain accuracy level, you get an evolved network. These hollow ones are the ones which are a legacy from a smaller network, which didn't do as well. So we needed to grow it a little bit more. We stop, of course, when we give it, enough is enough, some amount of time, or when it reaches accuracy, whichever is sooner. Okay, so if it reaches accuracy at some point, we declare it done, good enough. And if it doesn't, we let it go on, but up to a point. So this is the algorithm, starting with 2. So I already said this. Now let me, this is another picture of the same, but I thought I put it out a bit like this, and essentially start with 2, go through this particular growth algorithm and get a certain evolved network. Right. Okay. So now this thing, Manish did a lot of work. He actually tried 7 tasks. Okay, so he said, let me stress test this with 7 distinct tasks. 2 or 3 of them were in the same class, but of different levels of complexity. Okay, so the 7 of them were of 3 different classes, and each class had different levels of thing. One was what we would call a sine, well, he called it sine cosine. I didn't like it, but I went along with it. I didn't have a better word for it, I suppose. So this one was, given a sine, a function, you would have to predict or emulate another function which was a polynomial function of sines and cosines. Okay, so you would either, the simpler task is just to get a cosine out of sine, the other one is to get a complicated polynomial function of sines and cosines. And this is a pretty standard benchmark task. It's memoryless, but it helped us figure out things. And here, of course, things were very quick. We needed about 5 or 10 to get really low errors. So you can see this stuff here. which means the nodes are about 10, and this is the error which has plunged below, very low here. And of course, if you went a little bit more, you could get even better performance. So you start with something and you grow it and you get this one. The other one was, the one here is a forecasting task, again a standard benchmark. Manish had the usual Lorentz, he also had a Van der Pol, and he had a few others, but in the paper it's just the Lorentz and the Van der Pol. And the third task which he had and the third task, which is not here, but I will show you the results of, is what are called NARMA tasks. I don't know if you all have used this as a benchmark. So these are nonlinear autoregression moving average tasks. These are very useful tasks because it actually tests both the memory part, because the function is a function of the past inputs, and it has time lags of different orders. So we took 5, 10, 15. 15 is a pretty hard NARMA task actually. And we saw how well we could do with these increasingly complex tasks. And this has both a nonlinear function and also it has memory. So we had these 3 NARMA tasks as well. Okay, right. Oh, I'm brisk. Right. So this is just in words of what I just said. Now the pictures. Pictures speak more than words, or at least keep people a little more awake. So here it is. So this is a sort of summary picture. It's a bit busy, but I think you only need to carry away 2 or 3 things from this. Okay. The first thing is that here are the nodes that you need and where you end up when you have said that you have had good enough accuracy. Okay. So here are the iterations. It takes so many iterates to reach that final network size. So for instance, in the first sine cosine task, it really does it around 10. Okay. Actually, it did it around 5, but we scaled up the accuracy, and then this is a little bit more, maybe 20, and all of these are really pretty good. The NARMA tasks are always a bit harder. It's harder for any computing algorithm, and so these took more, but considerably less than other algorithms. Yeah.
Iterations are the number of cycles of the add.
Of the add and drop. Yeah.
So
yeah.
Potentially, an iteration doesn't increase the number of nodes.
Yes. In fact, at the end it stops. So That's a good question, because this might answer it. So. This doesn't answer it, but here, So for instance, here it has stopped in 10 steps. As much, and because it has reached its accuracy, it's good enough. And so basically in about 10 steps, it has grown roughly about from 2 to 10, and it's good enough, or 2 to 5. So it's actually pretty quick in the growth. Right. And this is the mean square error. And as you can see that these guys just become really good very soon. So just see how small these nodes are. This is actually 5, okay, 6, 7, 10, maybe 20, and any self-respecting guy doing thing will throw 100 or 200 in because you can, and why not? But you didn't need any of that. So when I saw the numbers, to be honest, I was a bit taken aback. I was expecting like 50 or 100. Okay, this is just pictorially those few of those tasks. This was the first 2 tasks. This was a reconstruction of the Lorentz and the Van der Pol. We took the one to be a limit cycle and one to be a chaotic attractor, just to mix things up. And these were the 3 NARMA tasks. This one was the hard one, 15th order NARMA task. And these are the 2 things which I already showed you. I've just stuck it in the side to make it there. Okay, this is just in words. Right. Now, I'll still spend a minute on this slide. It's a summary of that part. So there seems to be these small networks with just a few nodes which can efficiently process these complex tasks. This is what all that hard work of Manish seemed to demonstrate. And in some sense, a typical random reservoir would take for doing the equivalent task to the equivalent accuracy would have taken about 100 to 1,000 nodes. We just did the comparison. So it really works well. So now the next question. So that is a sort of applied-ish part. Okay, we can sell it saying, see, we've got a small network. So, that's nice. It costs less both in space and time. But now the question which I think physicsy people like, and the question is these, how these evolved networks, how are they different? Is there anything which sort of, pops out from these networks which looks different? Or, why is this slightly miraculous thing happening? Is it some black magic, or is there some property of this network which looks different? And of course, because, we like scaling laws, is there something which we can get? So to get that, the first thing we did was, we did the same tasks with 3 different things. So addition and deletion, I said, is what our, our framework is. But we tried 2 things just for comparison to give us a clue as to what may happen. One of them is uninformed. Okay, that's a reference which says every time I make it bigger. So every step it just increases. So my whole reservoir grows and grows and grows, and of course becomes very big. Okay, so N1, I know we don't have to remember this, but we had to call it something. So this is the uninformed completely. It's just bigger is better mode. The second one, there is feedback. In fact, we thought this was the one, but here there's feedback, and it says grow only if it helps performance. Okay, so addition module. So in some sense a partial one, and so it has the addition module. Okay, so it will expand it, but only contingent on improvement of the performance. Okay. Now here is what we get from the contrasting networks. These are the nodes, these are the iterations. This is for one task, NARMA 10, and N3, as you can see, is, so this is linear, which would be, at every step I keep adding 1, which is N1. Okay, so I keep, as iterates go on, I reach 500 iterates, size 500. Okay, but every other things, N2 and N3 are sublinear, so all of them are going to go to a smaller network. It's not going to keep growing with time. And as you can see, this one with addition and deletion, in fact, stops here because it has reached accuracy and doesn't need to grow any further. And these things are so much lower than the linear thing. Okay, so you do with much less. And the 3 tasks I have put in 3 panels. Only one you need to look at. The others look the same, so I can zip through them. So this first one I showed you, this is the linear part, the uninformed growth. This is growth with addition, no deletion, and the pink, I should have had a deeper pink maybe. Anyway, too late now. So this pale pink is the addition and deletion algorithm. Okay, and on the other side, we have the number of nodes it ends up with, the independent runs of these, right? And we end up with something. We start another batch, end up with something else. So we make a distribution of these. And you can see N3 is very tight. You end up with very similar kind of network sizes. Whereas with addition, you actually have a big stretch. There are some very small ones which are doing well, but some not so well, etc. And here too, in terms of the prediction, it's a very tight, it never does too badly. And so in that sense, it's nice because, you don't want to have a all over the place algorithm where, one time I get a small network, one time I get big network. So you want everything to be within maybe 5-10 of each other, which is more or less what it is. This is for the next task, pretty much the same story, and the next task. Okay, so this I wanted to spend a few minutes on. Now what is this colorful plot? So what I'm showing here, x-axis and y-axis, these are the nodes on the x-axis, and the density of your, so basically total number of links that you have in your system divided by n times n minus 1, like n square. And so that is on the y-axis. I have done it for 3 NARMA tasks because they are increasing complexity of the same type of tasks. So it helps us, fix a certain class of tasks. I mean, the paper has all the tasks. Now, there are some, so the color of the symbols is your error. So if something is blue or violet, it's good because it's very low error. Okay, so blue is low, red is high. So red and orange and yellow and all are bad, and violet is good. Okay, that's the first way to read this color part. The other part is you see that there are some symbols which are literally all over the place, little stuff. They are actually circles, though they probably you can't see it so well, and they are random networks, Erdos-Renyi random networks. So we took a whole bunch of 500 random networks, just generated it with different sizes over all these number of nodes, and we looked at the end result of what we got through the mean square error. And because the random networks are, as you can see, all over the place, which means some networks worked, some networks didn't, most networks didn't actually, and none of them are really very deep purple. 1 or 2 of them actually are, and they seem to fall on this rectangular parabola arm. And all the other N3, which is our addition deletion thing, falls along this arm. I don't know, does it look visible? There's a sort of dark colored arm in all of these pictures. That is where the error is low. So those are the good networks. So in this entire plane, you actually settle down to a curve, this rectangular parabola I called it, hyperbola. It's a rectangular hyperbolic arm, and so this arm is where it all settles down. So we think of this as a kind of scaling which has been respected by all the tasks. They all seem to fall along these things. But see, some of them are a very small number of nodes, some are slightly bigger nodes. Okay. And even when you look at a random, say you take a whole ensemble of random networks, you throw them at the job, some of them will do well with even small ones, some of them. But it's a huge task looking for it, because where do you search in this huge space for these very special ones? So this scaling is telling you don't search all over the place. Concentrate on that arm, on that very small region where these good random networks may be located. So it is giving you a pointer. The other thing, of course, is there by proxy. There is a sort of minimal bound to the size, and that is sort of a proxy for the complexity of the task. More complex, obviously the minimal bound is a little more. Okay. The other thing which we can look at is the scaling of the density with the size of the network. Now, here we'll have to fix ourselves to the algorithm. So what we are doing is here we are adding, and every time a node comes in, it makes a number of links which is, say, between some minimum and some maximum. So let's fix it. Maximum is, say, 5, minimum is, say, 1. So it could take 1, 2, 3, 4, 5 edges it forms, okay, when it comes in, the new node. Okay. So what would that sort of say? That if you have some kind of a density which would be like kind of the average, mean average degree of this network divided by n, then you would, because the mean average degree would be related to the mean of these connections it can make. That is to say, if it's 1 to 5, it's 3. So in some sense, you would expect a line to be 3 by n, okay, which is this line, this blue sort of line. But all these things are falling under it. Now, 1 is the minimum, and 1 and 5 are the minima and the maxima. Okay, so those are the two bounds, 1 by n and 5 by n. and the average would be 3 by n, but this actually falls below this. Okay, so what does this tell me? So it sort of tells me that the average degrees of the final networks is actually lower. And this is across all the 7 tasks of different complexities and different classes, memory, without memory, with nonlinearity, etc., etc. So for instance, here for N2, it's about 2.6. This is close to 3, 2.86. 3 would have been the average if it was all completely just a random sampling. And here it plunges below 2, it's about 1.9. So in some sense, there is one thing in these evolved things which says that you are actually coming to a lower degree, typically node. Okay? So it seems to actually be sparse. It's not so connected, tightly connected with each other. Okay? These were the things which popped at us, but the referee said, what about clustering coefficients? Since Manish did the job, I have a slide for that. I did not think it was so important. I still don't, but there it is. If you've done the job, you put, and it's in the paper. Now, in general, for a random network, it should have looked, the average clustering coefficient versus density should have been this line, straight line here. And for N0, which is your reference, or N1, which is essentially uninformed growth, it is like that. But for this addition and deletion thing, it actually deviates quite a bit from this. And how does it deviate? It gets lower. So in some sense, you are actually getting less clustered. Less average degree, less clustering is what seems to be doing the job. It's a smaller network with all of these also true. Okay? And with that scaling of node size versus density. So these were the things which we could sort of extract from it. It is possible that there are other things which we haven't noticed. Okay, so we haven't looked for it, but this is a sort of summary. So in some sense, there is a kind of hyperbolic arm which I showed with the scaling function, and also this relation between smaller, which is not I mean, it's actually going to be a little bit more deviated from Erdos-Renyi and actually lower in terms of clustering. Okay, last point. This is the last thing which we noticed, and I kind of like this, so let me just give 2 minutes and then I'm out. So the thing here is, this we actually noticed right in the beginning. So in this thing, you can actually, you say the nodes are coming in. You say that they have, say, probability half. They can be input nodes, or they can be output nodes. You remember that blob in the beginning, some stuff came in from input, some stuff went into outputs. So you say, okay, let's just run with this. Half of them randomly are input, half of them are output. So if you say that at the end of it, you should have 50% nodes which are input if everything just went according to random choice, and 50% would be output, which would mean about 50, half into half, about 25% would be both input and output, and 25% would be unique, as in not input, if it's output, not input, if it's input, not output. Okay, so all this should happen for a completely random thing. But what we find is a huge skew. Really a huge skew. So what happens is, instead of 50% having common readout and input, so instead of 50% being readout, it jumps to 75%. So it's not like 50 going to 55 or 60, it's significant. 3/4 it goes to, from half. And from 1/4 being common to input output, it again jumps to about 40%. Not quite half, but 40%. So significant difference. So there seems to be an asymmetric distribution of input receiving and output readout nodes in these evolved networks. This really seemed to be, there was a lot of work here done with a huge number of networks for all the tasks, and it was always true. Okay, and in some sense we found it interesting because somewhere somebody told us, oh, there are these there are these networks which are found, in various places where the readout nodes are actually, it's rich in readout nodes. Okay, so somehow it is selected out to have more readout nodes. We didn't select it out, but the evolution, this algorithm gave us a reservoir at the end with more of these. Okay. Okay. So this is my summary, and so I hope I sort of showed you this performance dependent network algorithm, and it stress test on a whole bunch of tasks, 7 of them actually, with different levels of complexity. And we sort of showed that they are actually significantly different from Erdos-Renyi random networks. I did not show it, but in the paper we've also given the p-values to show that it's a statistically significant. You can reject the null hypothesis there. It is not even remotely, you can't explain it through just a bunch of random networks. So it is really a different thing that pops out at the end. And so it's always doing this expansion and contraction till it's good enough, and it stops and its work is done. Okay, and it's sublinear growth, so which means it can saturate to a fairly small size, and very quickly actually. And there is this scaling law which we like, which because it tells us that in this huge space of possibilities which you can have if you just took a whole lot of random networks, this is a very special curve, and so it's actually if you were trying to just get it by brute force and blind search, you would probably do a bad job. Okay, so it's good to know where to look for these things. And this asymmetric distribution of the input and output nodes was also nice. Okay, that was it. I just okay, this so maybe in some sense, if you want to think of it, it gives you a little pointer about how to get a designer random network from, because it's sort of narrowing down your search space by giving you a scaling law, which is the end result actually, it's the observation. Okay, so that is it with this. I thought I'll just take 2 minutes to give a small elevator pitch of the next thing, which I will not explain, and but just to tell you that it exists. So this was with reservoir computing. So I asked my other group with which I do a lot of feed-forward neural networks to just try the same thing with a feed-forward neural network. This just trying thing was not so just. It was really a fair amount of work because these are very different algorithms. So what Anil did in this paper was to use gradient descent. It was not easy, so I will give him a lot of credit for putting this in, and I'll just show the end result. So this was done again. These are feed-forward neural networks. But again, we want to keep them small and dynamic. But what do you mean small and dynamic? So now, of course, there's back propagation. So you have to sort of put it inside your algorithm. And we found 2 ways of doing it. One was to make a sort of auxiliary weight, which is the network size. And it uses a loss, which is dependent on the size. And the second one was which is technically called a controller generated mask, which actually just modulates neuron participation. Okay, so basically one of them is a structural modification and the other one is activity modulation, but the activity modulation also just says this one has no activity, so it's out of the picture. So in a sense, both achieve this kind of thing of getting a smaller thing. And at the end of the day, this is the bottom line of that at the last slide, is that we could train and evaluate these neural networks on a bunch of tasks like nonlinear regression, like finding Bessel function and the usual benchmark tasks. Classification, he tried it with these cute spiral arms and doing all those different things. So all of these tasks were done, and they, in all of them, outperformed the static network. So it appears that growing networks too minimal or appropriate or optimal size is a better strategy. So let it grow naturally, start small, go to the amount that you need and stop. Somehow it's a better strategy than going large and pruning down, because when you are large, it depends on which one you start cutting. So this is my morales, and that is a good part at which to end. It was the timer?
No.
Oh, it wasn't the timer. Okay. Okay, right. So anyway, this was my last slide. So this was just to say that we also push the same idea to feed forward neural network. Okay, I'm done. Right.
Questions?
Yeah, Kathy. Yeah.
When your plot with nodes and iterations.
Sorry, yeah.
Everything's settling on this.
Yeah, I'll try and get that plot out. Yeah.
Is
Okay,
it dependent
surely.
on the
Sorry.
stopping criteria?
Okay, I'm frozen for some reason. Yeah, right. The scaling arm, that thing. Yeah.
So, you were plotting the final.
Fine.
Having reached.
Reached. Yeah, giving it some 500 steps or something. Yeah. Declared it done.
Where are they before they reach
how
that
do-
stopping criteria? Are they?
The stopping criteria.
They stop
Right.
and
Yeah.
You keep pushing it.
Correct. Yeah. So right. So yes. Or this one. Yeah. So the stopping criteria in the algorithm was just this. You go on for some number of steps, say 500, and if it reaches the accuracy it needs, good. If it doesn't, the algorithm stops wherever. So you might reach a accuracy which is not prescribed. It might be worse. But if you, if within those steps it has already reached the accuracy, then you stop. So some of them stopped very, very quickly, like they stopped, stopped right there in 10 steps. 10 steps, it got the accuracy which we prescribed it, and its job was done, and it delivered, and it was out. But some of them, I think we gave it like a 5,000 steps. So at the end, it went on a bit, but it may not have quite reached the accuracy of whatever we had prescribed it. That could also, especially the random networks, very often didn't reach the prescribed accuracy. They would need to go on a lot more. So whichever came first, your accuracy came first, your stop, or it stops at the end, whatever. I mean, we don't let it carry on beyond some number of steps. So in fact, that actually is a nice measure, because in that time given to it, a typical, for these tasks, a typical random network did not even reach that accuracy.
But so like, for example, in green diamond, if you kept going and iterating.
So all of them were iterated. Maximum number of steps was 5,000 here. After that, wherever it reached, and we declared it done. But it may have been 10 or 100, because it may have reached a network which gave the right accuracy, losses gone beyond, has fallen below the prescribed limit. So it stops there. Like any network, right? It goes on, you prescribe its accuracy, and then if it's reached it before that time, good. But if it hasn't reached it in 5,000 steps, you just stop it wherever it's reached. And that is some number, it has reached some node size, some predicted value. Some of them are a bit worse, as you can see. They're not as low, because at that point, it has still not reached such a good accuracy in the difficult tasks. It has reached some accuracy, but not as good. So if I wanted to get better accuracy, I would have to let it run a little more. It would have fallen a bit more, presumably. I'm not sure. But yeah, we give it some. So in the algorithm itself, it's there actually. If you see the algorithm, oh, this is up, sorry. It's right there in the algorithm. Yeah, oh, I didn't put it in the algorithm. Yeah, I did put, right. It's this box here. That's the stopping box. If error is less than epsilon to power, or if this, stop. That's the stop button. Does that answer your question? This purple box is the in the algorithm. I don't know. Is that mystifying? So at this point,
I'm more, sorry,
ha,
on the other figure, if you had,
ha.
like, if you look at, say, the green diamonds, if you keep iterating, do you add more knowledge?
Oh, you mean here? I mean these guys here?
Yeah.
Ha, right. No. Yeah. Okay, now I think I got your question. So you're saying if I let it go, would it become bigger and bigger? It wouldn't, because it has reached an accuracy. It will not, even if you add more, it is not going to be better, because you have said that if it has reached the accuracy, it stops, because that's all we need. So the accuracy is, say, 10 to the power minus 5 or some accuracy. So if it has reached it, you don't need to grow. But suppose my accuracy was 10 to the power minus 10, then it would keep adding a bit more to reach that accuracy. So here, even if I let it run for 100 more steps or 1,000 more steps, it will stay that same size of 5 or 10. It will not grow
I
anymore.
was wondering if you removed the condition, if you would approach like the sublinear situation that you saw in your second.
Yeah, right. Yep. This one?
Yeah.
Yeah, okay.
If you turn off your stopping criteria and if you come off that curve and stuff.
Right. So if you take off the stopping criteria, it's not you need to put some accuracy, right? I mean, in your loss thing. So you could, if I did that, all that would happen is, yes, it would grow a bit more, but you can't have a infinite accuracy. You have to give some number. So if the accuracy is really very accurate, say, as I said, 10 to the power minus 10, it would need to grow a bit more. So it would stick with the linear curve a little more and then turn off. So if I demand very high accuracy, it will go here and turn off. It will turn off at some point, but higher accuracy, it would need a bigger thing. So it will go linearly up to this point and then turn off, and then it will saturate. So here it saturates. It goes linear here almost for the first 2 steps, which is hardly, any 2 things is a straight line. So this is not meaningful, but this is additions only, okay? This is addition and deletion. That's really, truly sublinear. Here it sort of does a little linear. It's still actually always lower than linear, but then it turns in and saturates. These are just addition without deletion. And if I have uninformed, of course it's linear, because every time I'm adding. Uninformed is just linearly growing with time. Here it will turn off at some point, because it won't, after all, in the algorithm to add, you have the precision, right? Because error is better than something, only then add. You can put some number there, but whatever number you put, it's going to be satisfied at some point, and then it will stop growing, like it's big enough. So that is the big enough step. It will come out of the loop of addition or deletion. It will not touch it. In fact, it stops deleting even before it's, at some point, deleting it is also not necessary. So an addition, maybe a few more steps, it adds a bit more, but after that it just stops. You can run it for thousands of steps, it will stay the same. It won't matter. I don't know. We could discuss a little more later. Yeah, Kathy.
For the next talk. I was wondering that your final networks, you said that the connectivity was about 2, so they all had 2 links and a small clustering coefficient, which sounds like a ring. So coming from these time multiplex networks, where we also have
Yeah.
a ring network. So have you tried how a simple ring?
Yeah, no, it's not a simple ring. Yeah, of course, it is. I mean, he did try to visualize it. It was not a ring, but it was still. I mean, so it's not exactly 2, of course. It is 1.8 something. So it is. It was, well, I think that we did check to see if it was some structure which was identifiable. I can label it by something. Oh, then that it would be really interesting that at the end of all this we go from random to ring and then you're done. No, it wasn't that. It was still. it was still difficult to visualize the structure, but this much we could say that there was this asymmetry, and there was the scaling, and there was this lower degree and than a standard. These were statements. With a ring beating it, huh? That's actually a good question, and I don't know the answer to that. So you are asking if I just made a ring, who would I be? Yeah, I actually don't know the answer to that. I mean, I didn't try it. Yeah, I mean, yeah, I don't know if I should venture a guess, because I've been, yeah. I mean, I get your question. So.